All right, let's get started. My name is Cailin Smith. I'll be talking to you about the basics of how to write a compiler using LLVM. Obviously, in a talk for an hour long, I can't really go into a whole lot of detail. There's entire college curriculums, and you can spend a lifetime writing a programming language, right? So this is only the basics. It's a very high-level overview of what the general process is and how you get a binary at the end. First, though, who am I? I'm Cailin Smith. I am a senior software engineer at Microsoft by day. I don't work on any of this stuff, though, that I'm going to talk about there. I'm also the creator of the MethodScript programming language, and I'll go a little bit more into what MethodScript is, but it's I've spent the last decade working on that. It's an up-and-coming language that's somewhere between a toy language and an alpha release. Please do not use it for your production stuff. But if you play Minecraft, it's actually mostly, that's where its niche is right now. So if you run a Minecraft server, you may have heard of Command Helper, which is a plugin for the Java version of the Minecraft server, which allows you to run MethodScript in it. And that's where it's primarily used today. So I have a cool video, a Minecraft video, to show you in a little bit. But yeah, if you have a throwaway project or if you're just a language nerd, feel free to check it out. It's at methodscript.com. Most of the presentation is actually about LLVM, so yeah, we'll switch to C halfway even. So it's not just about MethodScript, but at least now you've heard of it. So here's the agenda. There's just a brief introduction of MethodScript and compilers in general, what they do. We'll talk about how you parse the program, whatever that is, into an abstract syntax tree, the AST. You'll see this term come up quite a lot. Then we'll take that AST and we'll compile it into LLVM code, and then object code, and finally a binary. And actually, most interestingly, the optimizations that LLVM does. I think that's a very interesting topic to kind of cover. So the objectives, there's a lot here, and not everybody is a language nerd. So is there anybody here who maintains their own compiler? One. All right, so yes, just us. So it's not exactly a popular thing to have to do, right? But there's nonetheless quite a lot in there. Does anybody write regex? Does anybody write complicated regex? Does anybody write complicated regex and then say, God, there's got to be a better way? Yes. So usually compilers are the answer to that. And compilers should not be this scary thing. They're not just for programming languages. You can write small domain-specific programming or compilers that work for whatever it is that you're trying to do. Parsing strings in general in a very generic and high-performant way is almost always better to do with a custom compiler than it is to use regex. Not that I'm suggesting you should throw away regex. It's useful and it has its place, but compilers are a good generic topic to know a bit about. And if you're a programmer, it's also good to know about these lower level optimizations that happen in the compiler. So pretty much every compiler is an optimizing compiler. So it's doing a lot of stuff to kind of retransform your code into something that's more performant. And it's important to kind of know what those optimizations are, or at least could be, so you can actually see the code that you write isn't what runs, it's the binary. And so knowing how you get from the code to the binary and what kind of things happen in there can be important for writing performant code. You don't want to over-optimize. You also don't want to sacrifice readability for optimization purposes when the compiler is just going to do that optimization anyways. So it's important to know this stuff even if you're not planning on writing a compiler. And if you are writing a compiler, talk to me after. So a few disclaimers here. I'm not an expert. I'm just 3 beginners in a trench coat when it comes to LLVM stuff. I don't know might be my answer for some questions that are specific about LLVM. A lot of the stuff that I do, I just copy from Clang without question, and some of it doesn't make sense to me, or I have a very, very basic understanding of what it is. So, but what I have works, at least, or what I've got in the slides I know about, but beyond that I might not be able to say a whole lot. Also, native MethodScript, which is compiling MethodScript to binaries rather than running it in Java, which I'll show you a diagram of later, That's just starting out, so we will swap to C midway. Also, the presentation uses LLVM 12, so the current version is 15. The stuff should all be still relevant, but just in case there's some differences, we're a few versions behind. So here's Hello World in MethodScript. So hopefully you can understand what's going on here. We're assigning a variable. We are printing that variable out. We're printing out a red Hello World. So there's a couple of functions here: string concatenation, assignment, variable interpolation. Basic stuff. This is about as basic as you can get without just messaging out a string. Here it is running in real life. So it is a real programming language, but we have a house here in Minecraft, and we hit the doorbell, and we get a text message. So it's mostly used in Minecraft, but it's unbounded. It is a real programming language. This is what the code for that looks like. It's very little code. So we're binding to the player interact event. If that event happened at a specific location in the game world, then we send an SMS, and that's it. So it's for what you get, it's a very straightforward language. It's easy to learn. I have a lot of people who have told me that they couldn't figure out JavaScript or whatever other language, and they played around with MethodScript, and especially in Minecraft, it's really, especially younger people, it's very motivating. So it's an educational language in that sense. So how is a MethodScript organized? We have the functions, which are the intermediate representation, the AST. There's a compiler that takes the source code and spits out this AST. There's tooling, so there's an IDE and stuff that kind of sits on top of that. These get output to the JVM, which is currently the reference implementation and the most complete implementation, and this is what's running in Minecraft. But what I wanted to do is that because this requires the JVM and Java and everything has to be installed, what I want to do is to actually compile to LLVM. When you compile to LLVM, you get native binaries for free, basically. So these are the platforms and the runtimes. And for the Minecraft stuff, there's Minecraft functions like setting, getting blocks, and whatever. That kind of sits on top of the JVM, but that's not really part of MethodScript. So a quick intro about LLVM. So there's several languages or compilers on the left here. These are the front ends. So Clang for C and C++, LLGo for Lang, and Rust C for Rust. And then on the other side, we have the targets, which are the CPU architectures. x86, ARM, PowerPC, M1s, all that's there. WASM is not really a CPU architecture, but I put it here because it is a target. So that's the WebAssembly, if you're familiar with that. It's different. It doesn't really belong in this list, but it's nonetheless got a backend in LLVM that's at least partially supported. You can do very real stuff with it, but it's kind of a newer technology, maybe not so mature. But before LLVM, this is what it would look like. So every compiler writer that wanted to target each of these CPU architectures would create a compiler for each of those. And each of these lines represents a lot of work. So if you wanted to support Intel and Mac and whatever else, you basically end up writing 2 or 3 compilers. Some of the work can be reused, but the actual conversion to the assembly or whatever, that's got to be redone each time. So this is just a lot of work. LLVM came in and said, no, this is too many lines. So we're going to get rid of all of these lines. We're going to sit in the middle, and you're going to target LLVM as a compiler writer, and we will target all of these targets as LLVM. And what's cool about this graph is, first of all, it's less lines in general. Each line still represents a lot of work, but there's less lines overall, and each person has to only deal with one line. So if you're a compiler writer, you just worry about writing your compiler. If you're a CPU architect, you worry about converting LLVM to your CPU, but there's this kind of standard abstraction layer sitting in the middle. So LLVM used to stand for low-level virtual machine. They want to be very clear that it no longer stands for that. It's just LLVM. And it makes sense because it is low-level, but it's not a virtual machine in any sense of that word. Maybe it was back when the project started or whatever, but it's just an abstraction layer between the compiler and the CPU. There's also lots of optimizations that LLVM provides. And what's really cool about these is that if you write a new optimization for LLVM code, everybody on the left and the right benefits from this. So it's actually really impactful if you can come up with some cool new optimization on LLVM stuff. Everybody in the whole ecosystem benefits from that. Microsoft and Google are really starting to bet big on LLVM as well. So Microsoft's using it for quantum computing projects. Clang is fully supported in Visual Studio now. Chrome has ditched MSVC for Clang on Windows. So these are real production projects. These aren't little toy projects or whatever. LLVM is really getting some real traction. It's actually been around for a while. It's been around since 2000 when it was very first started, but it's very hard to kind of break into this compiler space and get people to use your stuff, right? So it's been a bit, but it's coming along, and it's very much maturing these days. So you're all programmers, you know. Zero indexed and floating point means you can have quite a lot of numbers in between, right? So there's 3.0 easy steps to writing a compiler. First, step 0 is to design the language, and this is just left as an exercise for the reader. It's got an infinite number of points between there, though. The next step is to compile the AST, compile to LLVM IR, which IR is the intermediate representation. This is kind of the human-readable assembly. It's not really assembly, but it kind of looks like it. Or Bytecode. Bytecode and IR are one-to-one, but obviously for presentation purposes, it's much better to show you the IR, not the Bytecode. So I'll be using that. But those are interchangeable. And then finally, you use the LLVM toolchain to create the native binaries. So let's talk about compiling the AST. So what is an AST? What is an abstract syntax tree? So let's take the simple program 2 + 3 + 4. This is a program. We could also rewrite this as a prefix notation, also known as like a just regular function call. So we're calling the function add, and we're sending it the parameters 2, 3, and 4. And this is what the tree would look like for this program. So at the root, we have the function itself, and then any arguments that are passed are leaf nodes. The leaf nodes can also be other function calls as well, so it's not just, it doesn't have to be these atomic values or whatever. It can be much more complicated. But for this program, this is what the AST looks like. And this is kind of the data structure representation of a program. So how do we get that? The first step is to lex. So lexing is when you take the program and you read it in one character at a time. And the lexer knows about certain specific types of characters, like left parentheses and commas and things. So what it sees in this program is ADD, left parentheses, 2, 3, 4, right parentheses. It sees that A, D, and D go together. That's one lexeme, or one token. And so we create an identifier, is what this is called. And we actually need a bit more context to be able to say what it is identifying. That comes later in the parsing step. But we get each of these tokens here that are kind of combined into their logical lexeme. Next, the parser takes over, and it sees that there's an identifier here that's followed by a left parentheses. So that must mean that this is a function call. So we create the kind of top-level node there. Left parentheses means we start a new row on the tree, so we go down one level. If we encounter a right parentheses, we go up a level. Comma means start a new node on the same row. Conceptually, it's pretty simple to explain, I think. It can definitely be difficult. It's basically just a big switch statement in your lexer. There's a lot of other, you can generate, if you write a grammar, for instance, you can get these things for free, but I think it's just as easy to write the actual lexer yourself. So once you have this AST, it's just a tree in memory. The next thing to do is to compile it to LLVM IR, or the Bytecode directly if you're using the APIs and stuff. So the first step is to flatten the tree. This is basically just a depth-first recursion through the tree. So you get this flat structure here. And then we take this structure and we go from top to bottom and we create the IR. So each node is kind of handled independently from the rest. So in that previous tree that we had, what we're doing here is we're saying A, the local variable A equals the I32 2, B is 3, C is 4. The add function has to do an intermediate step because the add instruction provided by LLVM only does, you can only add 2 numbers at once. So we do add A and B, we store that into an intermediate, and then we do I, that intermediate, plus C, and then we store that into the result. So this is real LLVM IR. It's simplified in the sense that there's some boilerplate and stuff that I haven't shown you, but it's relatively straightforward to understand, especially for something this simple. And if you know any kind of assembly, you might be like, oh, yeah, I recognize this now. So here's the full program, and there's a lot of stuff here that you don't really need to know. The target data layout at the top is saying that we're using little endian, we're using Windows name mangling. Here's the alignment information. The target triple is interesting, though. This is what architecture we're targeting and tool chains and stuff that we're trying to emulate. We're creating a global variable here on this line here, where we store the constant string hello world, which is length 14 I8. It's an array of length 14 containing I8s. And it's a global variable. That's what the @ signs mean. We're defining a method here, main, and we take some arguments. These are argv and argc. Then we're calling puts. Puts is the C standard library way of writing to the console, and we're sending it. This is complicated, but we're basically getting a pointer to this string here. And so we're basically doing a system out here, and then we return 0. We also have a forward declaration of the puts because puts is defined in the C standard library. We are not defining it. So we're saying this will be here, the linker will fix it, so that the compiler can move on with its life. So here's a more complicated example. This is the rand function in MethodScript. So you'll note the red lines. It's kind of funny when you make a presentation, you look really, really critically about what you're putting in the slides. And I discovered a bug in MethodScript, so I fixed the bug, so these lines are not there anymore. But what's even funnier is when I get to the optimizations, we're going to come back to this example, it doesn't actually matter at all that I fixed the bug. But anyways, the red lines, just ignore those. So what we're doing, in MethodScript, rand with no parameters returns a value between 0 and 1, a double. So the C standard library provides the rand function, which returns an integer. And specifically on Windows, it returns a 16-bit integer, and I wanted more discrete steps there between each value. So what I'm doing is I'm calling rand twice, and then shifting left the first one, doing a bitwise OR with the second one, doing an unsigned int to floating point conversion of that value, and then dividing by the maximum rand number. So that gives us a number between 0 and 1. We're not doing anything with this value, so we're just returning 0 after. But let's do something with it now. And by the way, there's also the forward declaration here of this rand, because that's also provided by the standard library. So now let's actually output it. So this code here is the same as on that last slide, so don't get too hung up on that. I'll zoom in here. So what we're doing, this is a little bit complicated because we're converting MethodScript concepts into concepts that the C standard library can support. So it's not always like ideal or whatever. This is how you have to do it. So what we're doing is we're using sprintf to convert the decimal number into a string because we know we're about to output it, and we have to do that conversion first. So this is the sprintf. We're doing it in Aloka and all of this stuff. I'll explain Aloka later. But sprintf here is kind of storing the converted value into the buffer, and then we output the buffer. So now let's build on this a little bit more. So now we're going to call rand, store it in a variable, and then output that variable. And actually, yeah. So there's the same here as at the beginning and at the end. It's the same stuff, but we have this block here in the middle that's new. And I will zoom in on that. So what we're doing here, this assignment, alloca is an important call. This comes up quite a lot. So what this does is this allocates memory on the stack, and we are storing the value of the output from the previous operation in that stack, the memory that we've allocated on the stack, and then we're again loading it back into a register. So these are local variables, the 10 and 11. They're local variables, but LLVM allows us to kind of think of them as registers, and LLVM gives us an infinite number of them. Obviously, that's an abstraction. CPUs don't have an infinite number of registers, but we can think of the local variables as registers, and then whenever you're modifying something on the stack, you think of that as memory. But we'll come back to this when we get to the optimizations. So this is inefficient, though. This is weird, and it's inefficient. But the cool thing about it is that if we look at the actual code here, oops. So this is the rand function, or the output of the rand function. This is the output of the assignment function, and this is the output of sysout. And they're totally independent from each other. So as a compiler writer, I don't have to really worry about the interaction. I just have to do what the code said. And so I take the abstract syntax tree and I print it out. I do my own optimizations on top first, but once I have my optimized version, I don't have to go too crazy with it. So the next step, once you have this IR code, is quite straightforward. It's really just up to the LLVM toolchain after this. So there's kind of a lot here, so I'll focus on specific things. So the first step is to call LLC. This is the LLVM compiler. This takes as input the LL file, the IR that we had written, either by hand or through our compilation process. And we're saying we want an object file, and you do this on a per file basis. Then we call link, and you can use any system linker or whatever, but LLVM has its own, which is what I'm using here. We send it all of these object files that we had created, and we're linking it with the standard library. So this is where the rand and puts functions and everything else live in at least Windows in these lib files. Lib files, if you're familiar with DLLs, libs are the static include version of DLLs, basically. There's a lot of other stuff there that is, passed to things and whatever. Finally, we output main.exe. So this is the toolchain. So once you've got the IR written, this is what you run, and you get the binaries. And this works more or less the same on Linux and Mac and stuff. So that's it. That's how you write a compiler. But let's talk about some of these optimizations, because they're really, really cool. First, though, let's just review the memory model of a computer. So we have the physical layer here. The places that you can store memory in a computer, first is the CPU. There's also the CPU cache, L1, L2, and sometimes L3. And then finally RAM. And it goes from fastest to slowest. We don't really have a lot of visibility on the CPU cache. It just does that as part of the hardware. So we don't have a lot of visibility into that. But and then on the logical level, we have registers, the stack, and then the heap. All else being equal, if you can, if the thing that you're trying to do makes sense to do this for, you want to move that as far to the left as possible. So you would prefer that your memory is always coming from the CPU. If it must come from RAM, you would prefer it to come from the stack, and then finally the heap. Certain problems can't be solved. You can't store a dynamic array in the CPU, for instance. So some problems must be put in a certain location. But again, all else being equal, we want to move this as far to the left as possible, these memory accesses. So let's go back to this slide. So this is the rand and then sysout. So what we're going to do first is we're going to run the opt tool. So optimizations normally happen when you use the tool chain, assuming you don't say O0. But what we can do with the opt tools, we can run specific optimization passes. So there's a lot of them out there. But if we want to see each step one at a time, what the optimizations are doing, we can use this tool. What I'm doing here is I'm calling mem to reg, and it does what it sounds like. It moves any accesses that it can from memory, if we're using the stack, or then it's going to try and move those into register reads and writes instead. So this is the same program as before, but what you notice now is that I've basically, this is the rand call here, and this is the sysout call. We've kind of removed that middle inefficient section because we weren't actually needing to put that in the stack. It could have been in any value that's representable as an integer, including doubles, which are just basically integers with a fancy format. Those all lend themselves to being stored into the registers. And so LLVM saw that, and it said, okay, let's get rid of these and put them into the registers instead. You'll also notice that I'm using these monotonically increasing numbers on the left. That's because LLVM has this concept called static single assignment. And so what we can't do is we cannot assign a value into a register more than once. So you can kind of think of these values, the local variables, as constants. So you can only assign them once. You can change the value if they point to some value in memory. You can change the value of that memory, but you cannot reassign that register. It really is a weird way of thinking about things, but this is kind of what enables that abstraction of infinite registers and to be able to do some of these optimizations. So there's a really interesting Wikipedia article on static single assignment. If you're interested in this anyways, it's a good read. Yeah, so remember this Aloka store load pattern? What do you do if you have to write a value to it multiple times? So maybe you have an if block and some conditional. You either write one value or the next. That means you're going to have multiple stores there. But how do you do that? How do you move that to this kind of constant, everything's a constant thing? Well, let's take a look. So here's a simple C program. We're declaring I, and then based on some user input, we're either assigning 42 or 7 to it, and then we're returning it. So we're switching to C now. So let's use clang, and we'll tell it to do no optimizations at all, and this is what we get. This is complicated. Clang does a lot of extra stuff that I can't really explain, but I've annotated the important bits here. So there at 6 is the declaration of I. We're doing the if, the conditional in the if statement there in the next section here. So this is where we do, is argc greater than 1? If so, we store that to 8. Then if 8, we go to 9, else 10. In 9, we assign I to 42, go to 11 down here. And then the else block here is set I to 7, and then again go to 11. Then we load the value that was an I into 12, and then return 12. So how does it optimize this? So let's run mem to reg on this. So we have the same comparison here. This is the argc is less than 1, and then break and either go to 4 or 5. These are empty though, and we have this phi node. So a phi node is an interesting concept that kind of inverts your thinking on its head. So what a phi node says is what branch or what block did I just come from? And if I just came from block 4, then return the value 42. And if I just came from block 5, return the value 7. And that's what this output is helpful. This is provided by Clang. This is what Clang outputs. But that's why, because this says that from block 6, we either came from block 5 or 4, and from this block, we always came from block 2, which is an implied block 2 up here. So there's still some additional optimization to be done here, but this is how you do it. This is how LLVM does it. So we're back to not using the RAM anymore. It's all registers now. So this is really cool. The further optimizations, of course, we remove the empty branch statements there. And it doesn't even need a FI node in this case. A select is good enough, and select basically says if this value is true, return based on that. So let's talk about loop unrolling and instruction combination. This is a bit more complicated of an example. So here we have some code where we loop from 1 to 10 exclusive, and we increment argc, then we return argc. So what does this code look like without optimization? This is a lot of code. Sorry, I couldn't get it any shorter than this. But basically what we do is, this is the int I assignment in the for loop. Then we have the if I is less than 10 part. Then we do the guts of the for loop, which is adding 1 to I, or sorry, argc is what we had. Then we do the last step of the for, which is adding 1 to I, and then depending on the values, we loop back up to the conditional, or we exit. So there's a lot of stuff here that is kind of irrelevant, but we're basically doing some adds, more or less, right? So what if we do full optimizations? What do we get out of this? It's quite simple. So actually, this is a very contrived example. This is just a really fancy way to add 9. That's what we were doing, really. And LLVM saw right through that, and that's what it converted it to after the optimization. So how did it do this? This is actually a really cool trick. How does it know? Obviously, as humans, we can look at this code and say, oh, you're just adding 9. But how does the compiler get to this generically? Well, let's step through it one optimization at a time. So the first step to run is the mem to reg, which is pretty much a prerequisite for most other optimizations. This code, we end up with a couple of FI nodes here. We still have our add here. This is the adding 1 to argc. We also have the add for the counter variable here. This block 3 here is rather complicated and maybe not so necessary to fully understand. Let's do one more optimization, which is loop unroll. So loop unrolling is basically where you trade off program size for runtime complexity. So what we've basically done is we copy paste each internal of the loop 9 times, and so that's what's happened here. But we're still a long way from just add 9. So what's the next step? The next step is to do a simplified control flow graph. So what you notice here is that there's a lot of stuff here that's like we're just in block 10 and we go to 11. There's absolutely no need for this. So simplify CFG simplifies the control flow graph and gets rid of these unnecessary breaks, jumps and stuff. So this is kind of the core of the loop here. This is what we end up with. We add 1, add 1, add 1. The next step is to instruction combine. So we combine instructions that are basically the same. So in this case, it knows that the add instruction, if we do add 1, that's the same thing as doing add 2. If we do it 9 times, we get add 9. And that's it. Voila. So loop unrolling can't always be done. We cannot solve the halting problem. So the first example that I showed you was one extreme, which was a constant number of loop iterations. The other extreme is just who knows how many iterations. By the way, this is the output of that not optimized, and then the same process for this while user input. So the loop unroll does nothing, basically. And that's kind of what we expect. But there's kind of a middle ground here where we want to do some loop unrolling but not fully unroll it. And the reason that you would do this, actually these contrived examples, for the constant ones, obviously you can do that, but you don't always want to do loop unrolling. Sometimes it's less efficient, and that can happen if your loop repeat decision logic is very, very cheap and your innards are expensive, then there's probably not a whole lot of reason to do the loop unrolling. But if your decision logic is extremely expensive, then it actually makes quite a lot of sense to do loop unrolling. So I actually couldn't figure out how to get LLVM to show me an example of this, so I just took an example from Wikipedia of what loop unrolling is, and this is kind of written in a higher level language, but it's the same concept. So what we have here at the top is we've defined our bunch size as 8, and we do a modulo, a division, a floor division, and then a modulo to get the number of times we need to do the batch repeat, and that's what this is here. So in this case, 50 divided by 8 is 6, remainder 2. So we'll run this big loop here 6 times, and then we'll have some left over, in this case 2, and we use switch case fall through to jump down to 2, and then we do the remaining 2 there. So this is kind of loop unrolling in a more reasonable example. So LLVM contains a lot of optimization. So this is what you get when you do, actually I can't remember if this is 02 or 03, but it's a lot. It's a lot of optimizations. And actually, the ones that I've highlighted here are the ones that I just talked about. You'll notice that a lot of them are repeated. And that's because some of the optimizations will rewrite the code in such a way that now this previously run optimization can run again, and it will simplify it further. The general rule is, not always, of course, with CPU pipelining and whatever, there's some complexity in the statement, but as a general rule, the less instructions that you have, the more efficient your program is. So generally speaking, you want to simplify it as much as possible and just come up with the smallest file. Anyways, there's a lot in here. I don't know what half of these do, but this is what you get when you run 02 or 03. There's another tool in the opt tool, or another a mode or whatever in the opt tool that shows the control flow graph, which I think is an interesting thing to see. So this can show you your, optimized or not. If you use like GraphViz or whatever, you can see your control flow graph, which can maybe help you reason over what's going on in your program, especially if you're handwriting the IR and you want to see what's going on there. So the LLVM language reference is a great place to read about individual IR instructions. And if you're writing a language, then this is the bread and butter. This is the API. So you need to be very familiar with this because you're rewriting your language in terms of what LLVM provides you in the IR. It's changing constantly, so it's a bit of a moving target, and it's still very much in development. But it's actually a pretty good document there. There's some more references here for optimizations. There's, obviously you saw that big list. There's a huge number of them that I just didn't cover at all. Like I said, the SSA article on Wikipedia is really informative. LLVM is open source. It's on GitHub. This site here is really cool. So LLVM is quite low level in that it's very nearly assembly. And so there's a lot of concepts like throwing exceptions and whatever. One of the stated design goals of LLVM is to be able to target any architecture within reason, I guess. But not all architectures support things like exceptions and whatever, so LLVM does not provide that. So when you're mapping these kind of higher level concepts into this lower level, also doing things like changing if statements into jumps and things, this site here goes through that, about how conceptually you think about these things and how you convert this higher level stuff into a lower level language, in this case, LLVM. If you liked the Minecraft demo, so be sure to check out MethodScript. If you run a Minecraft server, it's definitely of interest to you. But if you like playing around with it, if you want to contribute as well, here's a link to giving any PRs or whatever, if you feel so inclined. But yes, so that's it for me. Are there any questions? Yes?
What's the difference between targeting the JVM and LLVM in MethodScript?
Yeah, so the question was, what's the difference between targeting the JVM and LLVM? So when you target the JVM, the AST is interpreted inside of Java. So the function rand is just a wrapper around Java's rand function, and it runs directly. So it's basically it is the runtime, and it interprets the AST. Whereas the LLVM, the output is an executable, and it's totally self-contained. So you don't need any Java or anything else.
Are there any plans to have JVM bytecode as a LLVM target?
So are there any plans for Java bytecode as an LLVM target? I don't think so. I would like to do that myself. So I could, in theory, I could put I could put any let me see if I can go back. I actually simplified this graph. I've used this in MethodScript pitch text before. There's another. You could put another leg here at the bottom for a DSL or whatever you want to, whatever thing you want to target. And so it targets JVM right now. It interprets in the JVM, but there's no reason I couldn't just output JVM bytecode myself. And a lot of the learnings from LLVM will certainly be useful there. But as a first implementation, running it as kind of in a it is compiled. It compiles to the AST, but then it's interpreted from there, and that's an easier thing to start with than a fully compiled language. But yes, it's less efficient to do that, and so it would be actually really great to be able to output the Java bytecode as well. Yes?
How does LLVM support multi-threading, like to ensure that the optimizations don't kill multi-threading?
Yeah. So the question was, how does LLVM support multi-threading? I think probably the answer is it doesn't. It's something that you have to manage yourself as the language designer. So far, I've not gotten into this because I'm focused on Hello World level right now. But I don't think I've not seen anything that specifically, because threads are a higher level concept that the OS kind of provides. So my suspicion would be that there's nothing specific in LLVM.
Just like in C, you would mark something as volatile.
Yeah.
You wouldn't be able to touch it, and memory barriers and stuff like that. And that
Yeah.
goes into the language, not necessarily the OS part.
Well, if it's using OS threads, it's going to have the contention resolution and things that are provided in the C library, basically, in the C standard library. So that's probably what the answer is that you use these things that are provided in the C standard library. But I don't know. Yes?
Do you know if there are any approaches or techniques that LLVM compiler devs can use to verify the correctness of optimizations?
Yes, there are. So what tools are available for verifying the optimizations? There's some bisection tools, for instance. So you run, you say, I found a bug, I think. I'm going to run half of the optimizations, and if the code output still works, it was in the other half, and then try again. I lurk in the IRC channel for LLVM, and that comes up from time to time that people are like, I think there's a bug in this optimization, and then that's basically the advice, is do this bisect, and then try and figure out which pass it is using this opt tool, basically, and then go from there, pretty much. So, yes?
How is the debug program? Does it provide some
Yes, debugging. So that is an interesting question. I've only scratched the surface, but what you can do is you can output. I don't think I have this in any examples actually, but you basically output dwarf information as part of the binary, yeah, I cut it out from this example. But you basically output extra information inside of the IR and inside of this file or through the Bytecode that says that, like, this line of code came from this source identifier or whatever, and then tools like the GNU debugger and stuff can just work with that. But I've only scratched the surface. Obviously, debugging is a super important thing to be able to do. So I very much want to provide that functionality at some point. but very, very surface level there.
Yes, you're actually on the right slide.
Oh, perfect.
Because you're providing some information there that is platform specific, right?
Yes.
In your IR.
Yeah.
But you said the whole point is to target the
Sort of. It's to not have to worry about the assembly for that architecture. So if you were writing bare metal, for instance, it should look the same in everything. But what we're doing here is we're using puts, for instance, that's implemented by Windows libraries or Linux or whatever. And so some of these vary. Like the rand function, for instance, returns a 16-bit value on Windows and 32-bit on Linux. So the IR does look different for each platform, and I do have to take those things into account. But at least the CPU-specific stuff should be the same. The only thing, in theory, if you're writing metal, the only difference should be this target triple. But yeah, there are platform differences still. So it's not a perfect abstraction.
Isn't the alignment maybe also something that you would have to be aware of?
Yes, yes. So what I'm doing right now is that I'm basically just copying what Clang is doing for alignment in each platform. But yeah, the alignment would probably be CPU specific as well. So, any other questions? Yes?
What about support for Unicode?
Support for Unicode. I don't know. So this is, yeah, that's a good question. I'm not sure. I think that's probably going to come down to, because you can put whatever you want here, and I think it's going to come down to whatever you support as the compiler. You're going to read in some text file, basically, and then you're going to output something else. So as long as you output something that this string can process, maybe you have to do escapes or whatever, then I guess it should be possible.
Doesn't Go support Unicode?
I don't know.
I think it does.
Yeah.
You can
Yeah, I'm sure that LLVM doesn't care, because you're just passing in these opaque strings from your language to the whatever the, like in this case, puts. So I'm sure it's basically up to you to support. Any other questions? Well, I'd like to thank you for your attention. I hope you got something out of this. You know, it's a kind of a niche topic, of course, but it's really great to see so many other language nerds here. So thank you all for your time.